Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 3 of 3 on the topic of multivariate analysis, and we'll discuss joint probability distributions and copulas. Let's get started. Despite there being an endless list of probability distributions for one variable, the list for multiple variables is much shorter and most of them are closely related. In most cases, we're going to show examples of bivariate distributions, that is, joint distributions with two variables, but in almost all cases, these examples can be extended to arbitrarily many variables. A joint distribution has to describe two things: the marginal behavior of each variable and the dependency or relationship between them. For two variables, this structure might seem pretty straightforward because the relationship between the variables might be simple. Adding many more variables means accounting for the interaction between all pairs of random variables. At the bottom is a sample of analytical multivariate models. The first is the multivariate normal, which is by far the most commonly used and easiest to apply. The remainder, including multivariate T, Dirichlet, and Wishart, are very rarely used except in Bayesian statistics. We are going to focus on the multivariate normal for two reasons. One, it's the most common and easy to apply of the multivariate distributions, and two, it can be used as part of a multivariate modeling tool called the Gaussian Copula, which lets us create a joint distribution of variables that have any marginal distribution that we want. Recall that the univariate normal distribution, the normal distribution we've seen so far, has two parameters, the mean and the variance. These are single values describing the location and scale of the distribution. When we extend this to a bivariate normal distribution, meaning it is the joint distribution of two variables, we expand the dimension of the parameters. The mean goes from a single value to a vector of length 2 that describes the mean of each of the two random variables being joined. The single value of the variance becomes a 2x2 covariance matrix, which describes the covariance between each of the variables being joined. As we extend the bivariate normal to arbitrarily many dimensions, the mu vector has length k, and the covariance matrix is a k by k matrix, where k is the number of variables being joined. The lower left shows a 2D density plot of a bivariate normal distribution. The density shows where combinations of x and y are the most likely as the height of the density. When samples are taken from the bivariate normal, they come out as a list of xy points. A k-variate normal would be a list of k-length vectors. For the bivariate case we are showing here, each point is a sample from the distribution. The right side shows a list of points sampled from the density on the left. If you take the mean of each column in this list, you get back the mean vector of the bivariate normal. If you compute the covariance between the two columns, you get the elements of the covariance matrix back. We introduced the parameters of the multivariate normal before, and here is an expansion of those parameters into matrix notation. The mean vector is simply a vector that contains the mean of each of the variables in the joint distribution. The covariance matrix is constructed so that each element is a covariance of a pair of variables. Let's look at the diagonal first. Notice that these are the variances for each of the random variables. This is because, as we recall, the covariance of a variable in itself is the variable's variance. Now let's look off diagonal. We see that for each row and column, that the value is the covariance of two of the variables. In row 1, column 2, it is the covariance of x1 and x2. For row 1, column 3, it is the covariance of x1 and x3, and so on. The matrix is symmetrical, so the value in row 3, column 1 is the same as row 1, column 3. When a sample is taken from the multivariate normal, it is a k-length vector containing samples from each of the k random variables. Each of the random variables is normally distributed and has a mean defined by the mean vector and a variance defined by the covariance vector. The joint distribution behavior becomes apparent only across a large number of samples. A single sample drawn from the distribution simply looks like a collection of normally distributed variables. Until you look at the covariance or correlation between these variables in a large sample, the joint distribution structure is not apparent. Recall that the standard normal distribution is a normal distribution with a mean of 0 and a variance of 1. The multivariate normal also has a standard version. The mean vector of a multivariate standard normal distribution is a k-length vector containing zeros. All of the variables have a mean of 0. The covariance matrix of the multivariate standard normal has 1s down the diagonal because each of the variables have a variance of 1. The off-diagonals are the correlation between each of the variables instead of the covariance. The covariance matrix of a multivariate standard normal is also sometimes called a correlation matrix. A sample from the multivariate standard normal distribution is a k-length vector of standard normal variates. Across a large number of samples, the correlation structure of this distribution becomes apparent. We went into a lot of depth about the multivariate normal because it's the most common and easy to use. The other three we mentioned before are the Multivariate T, which is a multivariate extension of Student's T distribution, the Dirichlet distribution, which is an extension of the beta distribution, and the Weishart distribution, which extends the gamma distribution. These aren't really commonly used except in Bayesian statistics. Each of the multivariate distributions can be very restrictive to use. It forces you to define the marginal distribution and joining behavior for each of the variables in a very specific way. Unless all of your variables have the same type of distribution and their joint behavior is easy to define, a multivariate distribution is unlikely to be easy to use. Scalars Theorem allows us to define multivariate distributions that have more flexible properties. First, it lets us use any probability distribution for each marginal distribution involved. This means that each variable can have a different marginal distribution. Second, it lets us define how the variables are joined together using a structure called a copula, which is only concerned with the joining structure and not with the marginals at all. This means that we can join together arbitrarily distributed variables using a structure that gives us the joint shape we want while preserving the behavior of each of the marginals. The two most common families of copulas are the Gaussian copula, which is based on the multivariate normal distribution that we spent some time with earlier, and the Archimedean copulas. The Gaussian copula is very straightforward to use because the relationship between variables can be defined using Pearson's correlation coefficient, and it provides a joint structure that is useful in a number of situations. The Archimedean copulas provide additional interesting shapes for the joining structure of the variables, and the strength of the relationship is usually measured with a single parameter that can be estimated using Kendall's tau. The Gaussian copula gets a lot of mileage for many uses, including the hydrologic sampler tool in the HEC-Watt software. The assumption for the Gaussian copula is that the joining structure looks like a multivariate normal, even when the marginals don't look normally distributed. It functions by taking random samples from a multivariate standard normal and converting the sampled marginal values from normal into a different distribution. We will show a demonstration of this sampling next. The Gaussian copula starts with a multivariate standard normal distribution like the density on the left. First, a sample is taken from this density, resulting in a vector of z values. Next, each z value is converted to a probability using the CDF of the standard normal distribution. From the extreme value theory discussion, we know that taking the CDF of a random sample of values from any distribution results in uniform 0, 1 random variables. This vector of uniform 0, 1 random variables is then converted into the target distribution marginals by using the inverse cumulative distribution function, also known as the quantile function, on each value. For example, if the first variable has a log normal distribution with some parameters, you would use the quantile function of a log normal distribution with those parameters on the uniform 0, 1 values to get a log normally distributed value. You would do this for each of the variables in your copula, and they may have different quantile functions. This results in a vector of values with the desired target distributions and a joining structure defined by the multivariate standard normal. Then, you can repeat this process a number of times to create your random sample. We will see the results of this process in action next. Here are 4 plots of bivariate standard normal noise with varying correlation between the two variables. The upper left is no correlation, upper right is positive 0.5, lower left is positive 0.9, and lower right is negative 0.5. These shapes should seem pretty familiar to you. These same shapes define the joining structure we get from a Gaussian copula, so you can see why these might be useful for a variety of situations. We will focus on the highly correlated cloud of points in the lower left as our copula. Imagine that we have generated 1,000 points from a bivariate standard normal distribution, and the result came out looking like this. This is the first step in using a Gaussian copula. The plot on the left is the same as the correlation equals 0.9 plot on the last slide. Notice that the values of x and y are z values. We can convert these to probabilities by taking the CDF of the standard normal. The plot on the right is what happens when we take each of the x and y and compute the cumulative probability using the standard normal CDF. Each of the values is now in the range 0 to 1 and has a uniform 0, 1 distribution. Let's define two distributions that we want our output to look like. Here are two density plots. Variable A is a positively skewed variable with a lower bound at 0 and no upper bound. Variable B is a negatively skewed variable with bounds at both 0 and 1. For each of these variables, we can turn U01 random variables into variables with a target distribution using the quantile function or inverse CDF. This is a property called the probability inverse transform. Inverse transform sampling is extremely common in statistical simulation. The U01 random variables we feed into the two quantile functions have been provided by the Gaussian copula, so we know that the underlying structure is bivariate normal with correlation 0.9. The resulting joint distribution is on the right. Notice how the density of the scatter for each axis reflects the densities. For x, more points are concentrated on the left than the right, and for y, more points are concentrated towards the top, the right side of the density, than the bottom, which is the left side of the density. In this video, we discussed joint probability distributions and copulas. Two key points to take away from this video are: the multivariate normal distribution is the most commonly used multivariate probability distribution, and copulas let us define a joint distribution made using arbitrary marginal distributions and some joining structure that gives us a desired shape for the overall relationship between the variables. Thanks, and come back soon to learn about other topics in our statistical methods and hydrology course.